Transmission. We will see steady state performance of transmission lines first. Steady state performance of transmission lines. Steady state performance of transmission lines. The single line diagram of power system is alternator, step up transformer, transmission line, step down transformer, load point. This is a single line diagram of power system. Initially it is synchronous generator or alternator. Synchronous generator, alternator. This is step up transformer, transmission line, step down transformer, load point. Now it is stator axis, rotor axis, load angle is delta. Load angle is delta. Already in electrical machines you have seen in alternator, stator and rotor angle in between stator and rotor is angle is delta. This is called as load angle delta. Now this is synchronous generator, transformer, transmission line. This is transformer, it is load, which is called as distribution transformer. This is called as power transformer. Nearer to the alternator is dealing with high voltage, which is also called as step up transformer, is called as power transformer. Nearer to the load, it is a step down the voltage, therefore it is called as distribution transformer or step down transformer. The main difference between machines already studied, the difference between distribution transformer and power transformer is, in distribution transformer rating is less than 1 MVA. MVA is nothing but capacity. If rating is less than 1 MVA, the transformer is called as distribution transformer. Now if rating is more than 1 MVA, that is called as power transformer. This is called as power transformer, this is called as distribution transformer. Always power transformers is connected nearer to the power plant because dealing with high ratings. Always distribution transformer is connected to nearer to our homes or to the load center because dealing with low voltage. It is step down transformer, it is step up transformer. Already we discussed single line diagram in basics. This is called as simplified single line diagram of power system. Now let us come to the discussion. Rotor angle. The rotor angle means delta. Rotor angle delta mainly influenced by characteristics of transmission lines. Rotor angle delta mainly influenced by characteristics of transmission lines when compared to characteristics of transformer. I will repeat once again. Rotor angle delta, that means rotor angle delta is mainly influenced by characteristics of transmission line when compared to characteristics of transformer because the faults are more common in transmission. Whenever fault is occurred, system will become unbalanced. Due to unbalance, rotor is accelerating or rotor is decelerating, by that load angle delta also changes. Therefore, when a fault is occurred, voltage in all the three phases will become unequal. Transmission is three phase lines RYB. Voltage will become unequal, currents becomes unequal. This is called as unbalanced system. Due to a fault, rotor axis swinging with respect to stator axis. When rotor axis changes, load angle delta also changes because of fault is occurred in the transmission line. But transformer faults are very less, therefore transformer is not influencing the rotor angle of the synchronous generator. Therefore, whenever transformer is not influencing the rotor angle of synchronous generator, I am ignoring transformer, I am connecting only transmission line. Therefore, alternator is directly connected to transformer because transmission line because transformer is ignored because rotor angle is less influenced by the transformer is mainly influenced by transmission line. Therefore, alternator is connected to transmission line. This is rotor axis, it is stator axis. Load angle between these two is delta. Now, it is sending end Vs, receiving end, sending end current is Vs, sending end current is Is, sending end voltage is Vs. This is receiving end side or load side. Therefore, voltage at the receiving end is Vr, current at the receiving end is IR. Current at the receiving end is IR. It is sending end VSIS, it is the receiving end VRIR. Receiving end VRIR. Now, transmission line parameters can be represented by either ABCD. Transmission lines can be represented by ABCD parameters, already networks you studied, or else is also one of the representation of transmission lines. Resistance, inductance, capacitance is also one of the representation of transmission line. Resistance, inductance, capacitance. Capacitor is a shunt element, resistor inductor is a series element. When come to the original explanation, I will explain why it is RL is series elements, C is shunt element. Now, for time being, trying to understand sending end voltage and sending end current is Vs and Is respectively. Receiving end voltage Vr, receiving end current is IR. Right? Tell me, sending end values is unknown values or receiving end values is unknown values? The unknown values are sending end side parameters, unknown values. This side is known values. This side is known values. Always receiving end parameters are known values and sending end parameters is unknown values. Unknown values will be represented in terms of known values by using ABCD parameters. Unknown values will be represented in terms of known values by using ABCD parameters. Let us come to the discussion why receiving end parameters is called as known values. See, Hyderabad is the city, or Delhi is the city, or Kolkata is the city, or Chennai is the metropolitan city, Bangalore. There are so many cities in India. Let us take Hyderabad. Without knowing the demand of Hyderabad city, without knowing the power demand of Hyderabad city, how power plant will generate electrical power? How power plant is generate electrical power? It is impossible. If it is generating power, suppose it is not sufficient to Hyderabad city, definitely it is a big problem to the government, present government. Or let us assume they are generating more power. Half of the power only we are utilizing, remaining half of the power is wasteless. There is something insufficient. Therefore, always based upon the load demand, by knowing the load demand, Hyderabad city demand, by knowing the Hyderabad city demand, we can generate certain amount of power. Therefore, the generation of the power totally depends on load demand. The generation of the power totally depends on load demand. The generation of the power is present in sending end side. The load demand is present in receiving end side. Therefore, generation of power is totally depends on load parameters or load demand. Therefore, these values are known values. Once this values is known, easily calculate these values, which is unknown parameters. That's why unknown values will be represented in terms of known values by using ABCD parameters. Therefore, if you develop the matrix, it is sending end side, unknown parameters, VSIS, it is ABCD, this is VRIR. Therefore, Vs is equal to AVR plus BIR, Is is equal to CVR plus DIR. Is is equal to CVR plus DIR. This unknown values is represented in terms of known values by using ABCD parameters. This is the representation of transmission, or else we can also represent transmission line by RLC model, or else ABCD networks. Now, we are discussing steady state performance of transmission lines. Now, let us come to the basic definitions. Later we will see all these things. We have much analysis. This is single line diagram of electrical power system. Now steady state performance of transmission lines. Transmission line performance can be analyzed by two ways. One is calculating efficiency. And other is calculating regulation. It is a percentage regulation represented by that symbol. Efficiency is represented by that symbol. Transmission line performance can be analyzed by calculating or evaluating efficiency and regulation. Let us take any electrical equipment. Performance can be analyzed two ways. One is efficiency, other is regulation. Regulation is of two types. One is voltage regulation. Second one is speed regulation. Any electrical equipment output is electrical. We are calculating voltage regulation. Let us take best example. Transformer is electrical equipment, right? Input is electrical, output also electrical, but in middle magnetic. Therefore output is electrical means in transformers what you calculated, in electrical machines voltage regulation. Now any electrical equipment output is mechanical. For that speed regulation is calculated. Any electrical equipment output is electrical, we are calculating voltage regulation. Any electrical equipment output is mechanical, we are calculating speed regulation. Now let us come to the transmission line. Alternator. Transmission is a three-phase. This is the load point. Sending end VSIS, receiving end VRIR. Power loss in this line is I square R. Transmission lines are there. From transmission lines we are not tapping power directly to our home. No electrical equipment can withstand for this one, because transmission is dealing with high voltage directly coming to our home. Everything will be smashed because high voltage. Domestic purpose we are using rated voltage 230 volts single phase, but from transmission line high voltage is coming directly to our home. All electrical equipments are damaged. We are ready to invest our next month's salary to purchase all electrical equipments. I hope you understand. Therefore from transmission lines tapping of power is impossible. When tapping of power is impossible, throughout the line current will be constant. Therefore current is not the deciding parameter to know the losses. Resistance is the deciding parameter to know the transmission losses. Resistance is the parameter to determine the power losses in transmission. Efficiency is equal to We know output by input into 100. Any electrical equipment which is producing output is electrical, for that we are calculating voltage regulation. Any electrical equipment which is producing output is mechanical, for that we are calculating speed regulation. Now in transmission line output is electrical, for that we are calculating voltage regulation and then efficiency. Transmission line performance can be evaluated by efficiency as well as voltage regulation because output is electrical. Now let us come to the discussion. Output is receiving end power, PR. Sending end power is input power. Output power is receiving end power by input power is sending end power into 100. This is the efficiency. Now percentage efficiency is equal to receiving end power by sending end power is equal to receiving end power plus losses in the line. Sending end power is equal to, already in machines also studied, input power is equal to output power plus losses. The output power, input power is PS, which is equal to output power is PR plus losses in the line is 3 into I square R into 100. 3 into I square R into 100. Therefore, efficiency is equal to receiving end power by receiving end power plus 3 into I square R. Now, efficiency depends, current is constant parameter. Therefore, in transmission, losses are decided by resistance but not current. Therefore, efficiency depends on only resistance of the line. Long transmission line, length is more, and long transmission line size of conductor also larger. That means area is large. Units of area is centimeter square or meter square. Length of the line is meters. Which is dominating? Area is dominating because meter square. Therefore, R is equal to rho L by A. Rho is constant. L is only meters. Area is dominating. When area is dominating, transmission line resistance is almost negligible. When transmission line resistance is negligible, the loss are also less. Therefore, transmission efficiency is 95 to 98%. Transmission line losses is 95 to 98%. Now let us come to the discussion. Transmission network is a three-phase network. By knowing efficiency of the system, it can understand how much amount of power loss present in the form of heat, because efficiency depends or losses depends on resistance. Resistance of long transmission line is very less. As resistance of long transmission line is very less, efficiency of the transmission network is high value, that is 95 to 98%. That means in transmission system losses are less, but where losses are more is distribution system. In distribution system, if you observe in your street, in your home, domestic purpose, in your street you observe, there will be two conductors. One is acts as a phase, other is acts as a neutral. In distribution system, there are two losses. One is improper loss. Second one is commercial loss. One is improper loss, other one is commercial loss. Now, tapping of power from distribution lines. This way we are tapping of power from distribution lines. With meter, tapping of power from distribution lines with meter. This is electrical meter. In your home, meter is fitted in between service lines, that means distribution lines, and your motor. This is called as service wires. The service lines are tapping power from distribution lines to your meter in your home, but that meter is not working, which is called as commercial loss. which is called as commercial loss, because you are doing some mechanism that energy meter aluminum disc is not rotating in your home in the meter, even though you are utilizing electrical power, but energy meter is not showing the readings. That means you are saving your money. This is called as commercial loss, is a loss to the government, right? Can I say tapping of power from distribution lines with meter, but meter is not working, which is called as commercial loss. Second one is tapping of power from distribution lines, tapping of power from distribution lines without meter, tapping of power from distribution lines without meter. Previously meter is there, but meter is not working because we are doing some mechanism to stop the energy meter, but electrical power is consuming. It is not showing the readings, but power is consuming. That is called as commercial loss. Other one is tapping of power from distribution lines without meter is called as improper loss. Generally in rural areas, very rural areas, some laborers are doing work during daytime. At the time they are removing the wires, service mains from the distribution lines. During daytime only engineers are visiting the places, or helpers are visiting the place. At the time there is no connection from home to the distribution lines. Evening 7 o'clock they are returning from the works to the home. At the time 1 or 2 hours they require some electrical power. During evening time they are tapping power, tapping these two lines to the distribution lines. Evening only, that means night time only they are getting power. At the time engineers are not working, not coming, or helpers are not visiting the rural areas. Once again next day morning they are removing these two conductors or these two service mains. Therefore the tapping of power from distribution lines without meter is called as commercial loss, improper loss. Therefore in distribution two types of loss will occur. One is commercial loss, other is improper loss. What is the commercial loss? Tapping of power from distribution lines, tapping of power from distribution lines with meter, but meter is not working, is called as commercial loss. Second one is tapping of power from distribution lines without meter is called as improper loss. Due to of these losses, distribution is having 8 to 10%. Distribution is having 8 to 10% losses. Efficiency of distribution system is 90 to 92%. This is distribution system efficiency. This is distribution system efficiency. And transmission efficiency is more, losses are less. In distribution losses are more because of these following reasons. Therefore total transmission and distribution losses. Transmission and distribution losses. In transmission what are the losses? 2 to 5%. 2 to 5%. In distribution what are the losses? 8 to 10%. Therefore total transmission distribution losses is 10% to 15%. Total transmission distribution losses is 10 to 15%. 10 to 15%. In distribution system losses are more. Next, regulation. Therefore transmission lines are working with high efficiency because losses are less, because efficiency depends on only resistance. Resistance of the line is very less due to large size of conductor. Next concept is regulation. Next concept is regulation. Let us draw transmission line once again. It is sending end voltage, sending end current. Transmission line represented by RLC. How RLC will form, I will explain. This is receiving end voltage, receiving end current is the load point. It is the load point. Now transmission line represented by three elements. One is resistance, inductance, capacitance. 3 is RLC. Already efficiency of the transmission line depends on resistance. Efficiency depends on resistance. Efficiency depends on resistance. Remaining two elements are there. One is inductance, other is capacitance. Input to the alternator is mechanical power. Input to the alternator is or generator is mechanical power. We are giving coal as input to the alternator in thermal plant. We are giving water as input in hydropower plant. All these are mechanical inputs. But what we are observing at the load point? Electrical output or mechanical output? Electrical output. Right? Regulation is defined as it is a change of voltage at the receiving end change of voltage at the receiving end from no load. No load means VR0. VR0 means no load receiving end voltage to full load, that is VR. What is the regulation? Change of voltage at the receiving end. Change of voltage at the receiving end from no load to full load while keeping sending end voltage constant. While keeping sending end voltage also constant and supply frequency made as constant. Supply frequency made as constant. Only under these two conditions we can define the regulation. What is the regulation? It is the change of voltage at the receiving end. Change of voltage at the receiving end from no load to full load. From no load to full load while keeping sending end voltage constant and supply frequency made as constant. Therefore, regulation is defined as percentage regulation is change of voltage from no load VR0 minus VR full load by full load VR into 100. Change of voltage at the receiving end from no load to full load while keeping sending end voltage constant, that is Vs is constant, sending end voltage constant and supply frequency as constant. Now how this two are maintained is constant is a important discussion. Now let us come to the discussion. Input to the alternator is mechanical power. Input to the alternator is mechanical power, that is represented by PS. Output of the system is electrical power. Output of the system is electrical power. As electrical output changes, that power loss is P is equal to input minus output. As electrical output increases, correspondingly mechanical input also increases, or PS minus P. If electrical output reducing, correspondingly mechanical input reducing, so that we are maintaining balance in between mechanical and electrical outputs. Therefore, power loss will become 0. Power loss will become 0. That means this is the synchronous machine. This is rotor axis, which is stator axis. Load angle is delta. Load angle is delta. As electrical output increasing, correspondingly mechanical input increases. As electrical output reducing, correspondingly mechanical input reducing. Therefore, we are maintaining balance between mechanical as well as electrical. Therefore, power loss is 0. When power loss 0, rotor axis not accelerating, rotor axis is not decelerating. Rotor axis is not accelerating, rotor axis not decelerating. Therefore, speed of the machine. Therefore, speed of the machine, synchronous speed means speed is constant. Whenever it is not accelerating or not decelerating, speed of the machine is constant. Therefore, speed of the machine is synchronous speed. N is equal to Ns, and N speed is synchronous speed. Now Ns is equal to 120 F by P. We know this formula, synchronous speed formula. As speed is synchronous speed, 120 is constant. 120 is constant. Number of poles also constant. Speed is constant. Definitely frequency also constant. In this way, we are maintaining frequency is constant. In this way, we are maintaining frequency constant. I will repeat once again. As electrical output increasing, correspondingly mechanical input also increases. As electrical output is reducing, correspondingly mechanical input also reducing. Therefore, we are maintaining balance between mechanical input as well as electrical output. Hence, power loss will become 0. When power loss is 0, rotor axis not accelerating, rotor axis not decelerating. Whenever rotor axis not accelerating, not decelerating, speed of the machine is synchronous speed. Speed of the machine is synchronous speed. Whenever machine speed is synchronism, synchronous speed formula we know 120 into frequency by poles. 120 is a fixed number, constant. Number of poles is always fixed in an electrical machine. Speed is already constant. Definitely we can also make frequency as constant. In this way, we are maintaining frequency as constant. However, excitation of alternator remains constant. This is excitation. Excitation we are maintaining constant. As excitation is constant, definitely sending end voltage also constant. At that time only we can define the change of voltage at the receiving end from no load to full load while keeping sending end voltage constant and supply frequency also constant. Sending end voltage constant, supply frequency is constant. Now, change of voltage from no load to full load is less. Change of voltage from no load to full load is less. Change of voltage from no load to full load is less. There is a less change in voltage at the output, therefore there is a better voltage at the output. See, in our home, voltage not fluctuating, always constant. Definitely our electrical equipments are operating effectively. If change of voltage is more, constantly in our homes voltage fluctuating, definitely electrical equipments will damage. Electrical equipments is damaged. We are ready to purchase all electrical equipments so that next month's salary is on the demand to purchase all electrical equipments. I hope you understand. What you understand is change of voltage from no load to full load is less. The regulation also less. Can I say there is a better voltage at the load point? If change of voltage from no load to full load is more, the change in voltage more means regulation also more. There is a very poor voltage present at the load point. Now, why change of voltage present at the load point is under no load condition. Under no load condition, capacitance dominant. Capacitance dominant. Therefore, voltage at the receiving end is greater than sending end voltage, which is called as Ferrand effect. Which is called as Ferrand effect. Under no load condition, capacitance dominant. Therefore, voltage at the receiving end is more than sending end voltage, which is called as Ferrand effect. Next, under full load condition, under full load condition, inductance is dominant. Inductance is dominant. Hence, voltage at the receiving end is less than sending end voltage. Because of inductor, voltage at the receiving end is less. Best example is our fan in the home. Above the fan is having coil. There are 3 blades like this. If you see the ceiling fan, there are three blades like this. 1, 2, 3 blades. In middle coil is there. Above coil one small white color box is placed, that is called as capacitor condenser. Remove that capacitor. The behavior of the coil is inductive. Switch on the electrical fan. Switch off the fan. Output is that voltage will be eating, inductor is eating. Therefore, speed of the fan is very less. Means because of inductive behavior, voltage at the load point is less. In order to improve the speed of the fan, we required more voltage, so that torque also increases. In order to provide more voltage at the fan coil, above the coil we are placing a capacitor. Therefore, capacitance will improve the voltage. Therefore, under no load condition, capacitance dominant. Already you know this. Because of this, voltage at the receiving end is more than sending end voltage. Sometimes under full load condition, inductance is dominant. Because of this, voltage at the receiving end is less than sending end voltage. One time it is more than sending end voltage, one time it is less than sending end voltage because of 2 elements, inductor and capacitor. Because of these 2 elements, one time it is more, one time is less. Therefore, the change of voltage always takes place because of inductor and capacitor. Can I say regulation depends on now inductance and capacitance of the line. Regulation depends inductance and capacitance of the line. Inductance and capacitance of the line. Efficiency depends on resistance of the line. Efficiency depends on regulation resistance of the line, but regulation depends on inductance and capacitance. High value of efficiency, system is excellent performance, and for better performance, regulation must be low value, means the change of voltage at the receiving end from no load to full load must be less value. Therefore, in order to declare the performance of transmission line is satisfactory, provided that efficiency must be high, and regulation must be low. Right? High value of efficiency always possible. Because resistance is less. And one more thing, efficiency depends only on resistance. Resistance of long lines always less. When resistance is less, efficiency is more. Therefore, high value of efficiency possible, but low value of regulation not possible. Reason, at no load condition, because of capacitance effect, voltage at the receiving end is more than sending end voltage. I hope you understand my point, right? See, high value of efficiency possible because resistance less. Because efficiency is inversely proportional to resistance, now only explained. But low value of regulation not possible. Reason why? Under no load condition, because of capacitance effect, voltage at the receiving end is very high voltage, which is more than sending end voltage. Therefore, the change of voltage is more, regulation also more. So, getting of low value of regulation is problem, but getting of high value of efficiency is simple. Therefore, transmission line performance mainly consideration on regulation, which is not possible. That's why we have to consider on that. To improve the performance, we have to maintain regulation must be low, but defaultly efficiency will become high. Therefore, In order to declare the performance of transmission line, efficiency must be high and regulation must be low. The important points is efficiency depends on resistance. Efficiency depends on resistance of the line. Efficiency depends on resistance of the line. Regulation depends on inductance and capacitance of the line. Regulation depends inductance and capacitance of the line. As resistance is less, efficiency is high, but low value of regulation not possible because of capacitance effect. Therefore, the performance of transmission line can be analyzed in terms of regulation of the line rather than efficiency. The performance of transmission line can be analyzed in terms of regulation of the line rather than efficiency. Why? Because of capacitance effect, voltage at the receiving end is more. Therefore, from no load to full load, change of voltage is more, regulation also more, which is creating a problem. But high value of efficiency is possible, but low value of regulation not possible because of capacitance effect. So the problem one is if regulation, that is the reason why transmission line performance can be analyzed based on regulation of the line rather than efficiency. Now, the transmission lines are different network models. The transmission lines are different network models, and the performance of transmission line can be analyzed. The performance of transmission line can be analyzed based on physical length of the line. Let's come to the discussion. Transmission lines are different line lengths. Hence, the performance of transmission line can be analyzed based on physical length of the line rather than wavelength. How it is means, input to the system is sinusoidal waveform. For one sinusoidal waveform, the wavelength formula is lambda is equal to c by f. For one sinusoidal waveform, the wave is travelled, we will say how many kilometers. Speed of the travelling wave is equal to light velocity. Light velocity is 3 into 10 power 5 kilometer per second. If it is in meters, 10 power 8. If it is in kilometer means 10 power 5 by frequency is 50 Hz. Therefore, velocity is 6000 kilometers. For one sinusoidal waveform, the wave is traveling 6000 kilometers. 6000 kilometers. But practically, physical length of the lines are very less. For one sinusoidal waveform, wave is traveled 6000 kilometers. Practically, physical length of the lines are very less. the physical length of the lines is either 150 kilometers or 180 kilometers or 250 kilometers maximum. The physical length of the lines is very less, but wavelength of the lines is 6000 kilometers. If you take from Kashmir to Kanyakumari, the length of the distance will be 3800 kilometers, but if you take throughout the India from Kanyakumari to Kashmir, distance is 3800 kilometers, but for one sinusoidal waveform variation, wave is travelled 6000 kilometers, 6000 kilometers. Therefore, transmission line performance can be analyzed based on physical length but not wavelength, because practically the length of the lines are not equal to wavelength. It will be physically either 100 kilometers or 150 kilometers or 250 kilometers. Therefore, transmission lines can be analyzed based on physical length of the line. They are, one is short transmission line, second one is medium transmission line, third one is long transmission line. Transmission line classification can be done based on physical length of the line but not wavelength. They are short transmission line, medium transmission line, long transmission line, short line, medium line, long line. That is up to 80 kilometers. Up to 80 kilometers it will be treated as short line. 80 to 160 kilometers in middle is treated as medium line. Greater than 160 kilometers is treated as long line. Greater than 160 kilometers is treated as long line. So up to 80 kilometers is treated as short transmission line. 80 to 160 kilometers is treated as medium line. Greater than 160 kilometers is treated as long line. Right? Therefore, it is defined based on only frequency is 50 Hz. For other frequency it is not valid. Only 50 Hz frequency the classification is valid. Only 50 Hz frequency classification is valid, but other frequencies classification is not valid. Therefore, transmission line classified based on physical length, which will be short line, medium line, long line. Up to 80 it is treated as short line. 80 to 160 is treated as medium line. More than 160 is treated as long line. More than 160 is treated as long line. Now, let us come to the discussion. Transmission lines are classified based on physical length of the line rather than wavelength. Fine. Therefore, we are dividing transmission lines as three types. One is short line, second one is medium line, third one is long line. Now, transmission lines connected to bus bar. This is the alternator. Every component of power system is connected with the help of circuit breaker and relay. This is circuit breaker as well as switch. Circuit breaker acts as a switch. Every component of power system is connected with the help of circuit breaker and relay. Now, it is resistance, inductance, capacitance. This is the load point. When switch is closed, short and medium lines will take less time to charge the line. When switch is closed, short and medium lines will take less time to charge the line because of short length. When compared to long line. Whenever they are taking less time to charge the line, that will be represented by steady state behavior. This is short line, medium lines. When switch is closed, the short and medium lines will take less time to charge the line. You are settling in the classroom with less time. Automatically system is under steady state. You are taking more time to settle in the class, it is under transient state. Now, because of less distance when compared to long transmission line, the short and medium lines will take less time to charge the line. Whenever these two are taking less time to charge the line, that will be represented by steady state behavior. Next, long transmission line. Whenever switch is closed, due to long length of the line, long transmission line will take more time to charge the line. Therefore, long transmission line will be represented by transient behavior. Once again I will repeat. Due to long transmission line, when switch is closed, it takes more time to charge the line. Therefore, long transmission line will be represented by transient behavior, whereas short and medium lines is represented by steady state behavior. Therefore, It is short transmission line, medium transmission line, long transmission line. Short transmission line, medium transmission line, long transmission line. Short transmission line, only elements are represented as R, L and C is approximately 0. Medium lines are represented as R, L, C. Long lines is represented as R, L, C. Long lines is represented as R, L, C. Medium lines are represented as R, L, C. Short lines only represented by R and L, but C is equal to 0. C is equal to 0. Why capacitance neglected in short line means, due to short length of the line, for analysis purpose I make capacitance approximately 0. Short length means capacitance formation also less, therefore capacitance will be neglected in short line for analysis only, but medium and long lines will be taken as RLC, RLC. Now, whenever it is taking less time, the short transmission line represented by steady state behavior, short transmission line represented by steady state behavior is also steady state behavior, but long transmission will take more time, hence it will be represented by transient behavior. Hence it will be represented by transient behavior. For steady state behavior, we are using lumped parameters. Lumped parameter means resistance, inductance, capacitance physically separated. That is called as lumped parameters for steady state to apply KVL and KCL. Lumped parameters, transient state can be represented by distributed parameters. Distributed in the sense resistance combined, inductance combined, capacitance combined. All three are together, all which is physically not separated. Resistance mixing, inductance mixing, capacitance mixing, all these three are together. That is, behavior is nothing but distributed behavior. That is, behavior is distributed behavior. Now, as long transmission is transient behavior means we have to use distributed elements. That means RLC physically combined, where lumped parameters R, LC are physically separated, and for lumped parameters we are using KCL and KVL. For lumped parameters we are using KCL and KVL. Here also KCL and KVL. For distributed parameters we are using mathematical model. For distributed parameters we are using mathematical model. Right? This is the small understanding of short, medium, long lines. Now we will see which line is having more resistance, which line is having more less resistance, which line is having more capacitance and which line is having less capacitance. We will see all these things now. Now let us come to the discussion. Short transmission line capacitance is neglected. Medium line all elements are considered. Long line also all elements are considered. Therefore short line is represented by steady state behavior. Medium line is represented by steady state behavior. Long line is represented by transient behavior because it is take more time to charge the line due to long length. Therefore steady state means lumped representation. Transient means distributed representation. For lumped elements we are using KCL and KVL. For distributed we are using mathematical model. For distributed we are using mathematical model. Now one more analysis. Short transmission line, size of conductor is less and then area of conductor also less. Long line is dealing with high voltage, definitely area of size of conductor is more. Therefore area of size of conductor is less in short transmission line. Long transmission is area of size of conductor is more, which is in medium line. Medium resistance R is equal to, we know, rho L by A. As area is less, resistance more. Resistance is more in short line because of area less. Long line is resistance less. Medium line resistance is medium. And efficiency is inversely proportional to resistance. As resistance more, efficiency less. Efficiency less here. Less means let 95%. As resistance is less here, efficiency is more in long line. Therefore it is more efficiency, 98%. Therefore medium line is in middle of 95 and 98%. Medium line is efficiency is 95 to 98%. Now coming to capacitance. Capacitance, length of the line is more. If length of the line is more in long line, as length of the line goes on increasing, capacitance is also parallelly developing. Capacitance parallelly developing. Capacitance parallelly developing. As length of the line is more, capacitance also more. Therefore capacitance more in long line because of more length. capacitance almost negligible because of short length and short transmission line, capacitance medium here. Now capacitance medium means, what about regulation here? Now as capacitance more, voltage at the receiving end is more, therefore change of voltage from no load to full load is more, hence it is regulation also more. Capacitance less means change of voltage from no load to full load is also less, therefore regulation is less. Here regulation is medium. Now short transmission line will have less efficiency, less regulation, but already explained performance of transmission line mainly explained by the regulation rather than efficiency. The line which is having less regulation is the excellent line. The line which is having more regulation is the worst line. Therefore, short transmission line is having less regulation is the excellent performance when compared to long line. But practically we are using long lines but not short lines. Therefore, we have to discuss about long line performance, how to increase in stability. But right now the point is, long transmission line is having more regulation because more capacitance. Short transmission line is having less regulation because of less capacitance. Less regulation because of less capacitance. Therefore, short transmission line performance is better than long transmission line. Short transmission line performance is better than long transmission line.